Okay, conservation of energy. Here we have a spring, 1 kilogram object, spring constant of 400 newtons per meter. It is pulled down 0.1 meters, 10 centimeters, so that's our x, and then it is let to go into periodic motion, harmonic motion. So the question is, what is the speed when it gets back to equilibrium? Equilibrium is back when it's here. So basically all the spring potential energy that got stored in it is becoming all kinetic energy when it gets here. So we just make a simple energy argument. So we got PE spring equals KE, 1/2 KX squared equals 1/2 MV squared. The 1/2s go away. K is 400. This is 0.1 squared. This is 1 V squared. And when you math that all, you end up with 2 meters per second. Okay, next. 2 different ways of doing this one. It starts at 0. It goes to 30 in a time of 6. Question is, what is D? Well, we can find A and then do kinematics, which is a perfectly acceptable way of doing this. So we say VF equals VI plus AT. VF is 30, VI is 0. A times 6 seconds. A ends up being 5. Then we go and we use the distance formula. So D equals VIT plus 1/2 AT squared. So D equals 0, 1/2, 5 times 6 squared gives you 90. Or the other way you can do is, since it explicitly says it's a uniform acceleration, we could take advantage of the fact that the average velocity is equal to d over t. The average velocity would be the average of 30 and 0, which is 15. Then we have d over 6. And, nicely enough, that also turns out to be 90. This one is mostly a concept question. If we have a path that looks like this, at the top it is only moving the x direction. And if we remember, if this is v naught, and we're looking for v in the x direction, it's just v naught cos theta. And we also know that at the top, it still has acceleration due to gravity of g, which is 9.8 meters per second squared. So that's why it's d. Okay, now this guy. This guy is simple enough, but I guess we'll go over it real quick. Launched from 2 meters in the air, goes up 3 meters, comes back down 5 meters, and the question is where is it relative to where it started? Well, it's 2 meters below where it started, so 2 meters below. Okay, these number 5 and 6 got thrown in here. I guess I should have probably done this in a slightly different order, but it is what it is. So this guy is Fg, this is Fr. So if we have force of gravity that's downwards, and Fr, which is based on negative BAV, shortly after it left, V is very small, so this would be very small, and it's obvious in the opposing direction of the force of gravity. When it gets to terminal velocity, we have Fr and Fg, which are equal to each other. That's why terminal velocity occurs, because it's when the net force is 0, and that means the acceleration is 0, hence terminal velocity. Okay. Now, the other A, I don't know why it did it this way. The way we're going to do that is that's going to be setting these two guys equal to each other. So we get FG and FR. Kind of made mention of the fact that's the case here. Okay, so we got MG, B, A, V. Now, technically these are both negative. We want to go that crazy, but we don't have to. So V ends up giving us MG over BA. Now, actual B. Actual B is kind of a pain. So what I did is I actually put it on a page. I cut and pasted it onto the page. So I'll walk you through it. F equals MA, which is equal to MG minus BAV, right? So they're allowing downwards in this particular case to be the positive direction and upwards to be the negative direction, which is perfectly fine. We've done this before. Now, they then said M dV dt. So they just made this into what it's equivalent to, which is the dV dt, mg minus BAV. Now, they solved the differential. So basically what they did by doing that is they put all the v's on one side and the t's on the other side. Then they do from 0 to v, they're doing the integral. So we got the integral of the left-hand side, integral of the right-hand side. Now, integral of the left-hand side takes some work because you have to do some U substitution. So I'll give you a second to look at that. Ultimately, when you do the U substitution, the way they give it to you, it ends up giving you this, right? Negative ln, vt minus v, then you evaluate it based on the bounds. You get ln vt minus v minus ln of vt equals negative ba over m t. Use our rules for finding the difference of natural logs, and you get this and this. Then you do you raise both sides to e, or e to both sides. We get rid of the ln here, e to the negative bat over m. Do a little bit of algebra, and we end up with this guy right here. Again, this is a video, so you can pause it here. You can look at this. You can take as much time as you need to look at it. It's a reasonably simple calculus question, if that's actually a statement that makes sense. Okay, over here. So the acceleration, if we're talking magnitude of the acceleration, it starts at g, and it goes down like that. Now, if we're not talking magnitude, it would start at g, which would be negative, and go like that. Ooh. Like that. Okay. Now the velocity, again, if we're talking about magnitude, would be at 0. We get faster and faster and faster, but level off at vt. If we're not talking magnitude, then it's going to look like this, and level off at negative vt. Question 8. Okay, question 8 was tricky. 6 rather, sorry. Slide 8, I apologize. Okay, so for A, it says, does the magnitude of the acceleration of the ball increase, decrease, or remain the same as the ball moves upwards? Okay, so here's the trick. As the ball is moving upwards, the force acting against it, the air resistance, so we'll call it force R, like the last question did, and force gravity, are both acting in the same direction. Now, we know that Fr is based on kV, right? Negative kV. So, as V gets smaller, R gets smaller. So, if my net force is Fr, negative Fr plus negative Fg equals 0, both of them are acting downwards. This one's not changing, but this one is getting smaller. Oh, not equal to 0, sorry. It's equal to ma. So, if both of these are acting downwards, but this guy's getting smaller, the net is getting smaller. And since mass can't be changing, that means acceleration must be getting smaller. Tricky one. Now, B says write, but do not solve a differential equation for the instantaneous speed v of the ball in terms of t as the ball moves upwards. Well, it's basically just taking advantage of what we just wrote out already. Let me erase this. There's got to be a quicker way to do that, but I haven't found it yet. So we have minus FR minus FG equals MA. So minus FR is going to be minus KV minus MG equals M dV dt. And as soon as you have this guy in here, surprisingly enough, we're done. Okay, determine a terminal velocity. This is very similar to the last question. So I'm going to erase this. And we have C. Terminal velocity is going to occur, so now we're talking about when it's on its way back down. So when it's on its way back down, the force of resistance is going to be this way, and the force of gravity is going to be this way, and terminal velocity occurs when they are equal to each other. So we're going to say KV equals mg, v equals mg over k. Cool? Okay. Now D. Does it take longer for the ball to rise to its maximum height or to fall from the maximum height to the height from which it is thrown? Well, that's a great question. Let me erase this real quick. So on the way up, it's losing energy, right? Now, the question is it losing more energy on the way down or on the way up? So on the way up, it's losing energy, but it's losing energy, and this is going to sound crazy, at a lesser rate than it is on the way down. So it's actually going to take longer to go up than it is to go down. I have a feeling that's going to be one we're going to have to talk about on Monday, but we're going to move on. Where are we? Okay. So now this, the velocity. Well, the velocity should look like this. Getting to VT eventually, starting at V naught, and that's the halfway point in terms of time, so this guy should be shifted ever so slightly to the left. Okay. Back to the multiple choice question. So, boat moves across the river's velocity relative to land is VRL, and the boat's velocity relative to the river is VBR, which of the following represents the velocity of the boat relative to land? Well, that ends up being much easier than you would think, because it's just that guy. It's just the sum of the two of them. Since they're writing in a vector notation, no need for Pythagorean theorem or anything crazy like that. This guy. Oh, that's the same guy. Okay, this one. Cars traveling along a straight level road when it runs out of gas at time equals 0. From this time on, the net force on the car is this. So we've kind of already done this. So I didn't write all the choices just because it took up a lot of room. So I only wrote the right answer. Now the right answer is going to be, it's going to be moving forward at some speed, and it's going to slowly go towards 0. Displacement is going to continue to move forward, but at a lesser and lesser rate. That would make sense based on what we know about derivatives. Okay. This guy. Okay. So we got a car traveling down the highway at a speed v when the driver slams on the brakes and skids to a stop in a distance of d. Assuming the same frictional force, how far would the car slide if the speed was 2v? All right, so, if we look at VF squared equals VI squared plus 2AD. Now, if we start off with VF squared being 0, VI being 1, 2 times 1 times D. Now, I'm going to make this 1. Oh, I'm going to make this -1 technically, because we're just doing a comparison method question. Now, we know that the force of friction would be our MA, and we could do all that math, but at the end of the day, it's just a set value based on a constant force. So when we do all this, we bring this over, we get -1 equals -2D, D equals 1/2. That's my initial scenario. Okay. Now, how does that compare to the second scenario? Well, in the second scenario, we have the same formula. I'll leave this up. VF squared, VI squared, plus 2AD. Okay. VF is still 0. This is going to be 2V. So, instead of writing 1, I'm going to let this be 2 squared plus 2 -1D. Well, I bring this guy over. It becomes -4 divided by -2 equals D. D equals 2. Now, how does 2 compare to 1/2? It is 4 times larger. So my new D is 4 times bigger than my original D. So that's why it's going to be 4D. Moving on. Okay. Projectile is launched from level ground with an initial velocity V0 at an angle of theta. If air resistance is negligible, yada, 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 how long would a projectile remain in the air? Well, we have V final equals V initial plus AT. Now, we know that V final is going to be -V0, and this is going to be V0 plus AT, right? Now, this A is going to be G, right? I want to argue. It's going to technically be -G. So we'll bring this guy over by subtracting -V. So that gives me -2V0 over -GT divided by -G, and we end up with 2V0 over G. Now, the only problem is this is not just being thrown straight up in the air, it's being thrown at an angle. So that V0 that I've been using really needs to be V0 in the y direction, which is going to be V0 sine theta, which makes this V0 sine theta, which ends up giving us E. Next one. Plane starts at rest on a runway. First 30 seconds, the plane's acceleration is given by the function of. So they give us acceleration is beta t squared. They tell us what beta is, which we'll get into in a minute. What is the plane's speed at t equals 30 seconds? So to go from A to V, we have to do the integral. So we got beta t cubed over 3. Okay. Once we do that, we just can plug in the value they give us, which is 30 seconds. So we got 1 over 90, which is what they told us beta was. We have 30 cubed over 3. The bottom ends up being 270. The top ends up being 27,000. This and this become 1. And we end up with an answer of 100. Okay, now I'm going to, for now, skip this one because this one actually ended up having information on it about rotation. And remember, we talked about today that rotation is not actually going to be on the test. So we're going to ignore this one for now. We'll come back after April 3rd if necessary. Okay, so now, question 14. Again, I just wrote the proper answer in here. So it says a cart moving in a positive x direction and passes the origin at time equals 0. Car then moves at a decreasing speed, stops, and moves in the negative x direction. So if we're looking for speed on an x versus t graph, we're looking at the slope. So it's something that has to start with a positive slope, which it does. Has to have a decreasing slope that at some point gets to 0, and then has to have an increasing negative slope, which is why A is our answer. Now, 15 and 16 were kind of interesting because it gives us these 5 different choices of pairs of motion for x direction and y direction. Now, the first one says, choose the pair of equations that best answers each question. Well then, where are we? I eliminated the question. Okay, so the question was, if I remember correctly, the object is moving with a constant velocity in both the x and the y direction. If it's moving at a constant velocity in both the x and the y direction, the displacement has to be solely based on t. It has to be a linear function with t. So every second it takes by, it's covering the same distance. Same thing here. But every second it takes by, it has to be covering the same distance. Next one. Wait. But there's more than one of these. I somehow skipped 16. Well, no bother. 16 was very similar. The only difference is I believe the answer for 16 was this one because it said it was moving at a constant speed in the x direction, which means it's this, but is constantly decreasing its velocity in the y direction. So really, the best way to do this is to think of this as a situation where an object is moving under the force of gravity. So the answer for 17, even though, or 16 rather, even though for some reason it got skipped here, is going to be E. Again, if we need to talk about this on Monday, we will. Okay, 17. Two objects dropped from the same, from rest from the same height. Object A falls through a distance of dA during a time of t. Object B falls a distance of dB during time of 2t. What's the relationship between the two? So we're going to do this the same way as we did before. So we're going to say BIT plus 1/2 AT squared. And we're going to do the comparison method. So I'm going to start with, or the double triple half as Mr. K likes to call it. So we're going to start with D. Now, we're going to start with the initial ones. We're looking for dA. We're going to let this be dA. So it starts at 0, 1/2. Now, because I can choose these to be anything I want, I'm just going to pretend like A is 2. It'll just make math easier. And we'll let the initial time be 1 second. So half of 2 is 1, 1 squared. This guy is 1. Okay, now dB, D equals, the initial velocity is still 0. It's falling in the same universe, so we're going to still let that be 2. But now it's falling for twice the length of time. So that's 1. That's 4. So D equals 4. So in comparison to dA being 1, dB is 4 times that. So dA is therefore 1/4 of dB. Okay, 18. Two particles are launched with the same initial speed from the same location, one at 30 degrees, one at 60 degrees. All right, this one if we're being completely honest. This one's a pretty simple concept question. So if something's launched at 30 degrees, if we just draw the picture, 30 degrees versus 60 degrees. Now, hopefully you remember this fact, that the distance they both travel in the x direction will be the same because they are the same distance from 45, or because they both add up to 90 degrees. However it is, your teacher or myself explained this when we did it. Okay, so time in the air. Time in the air for the 60 degree one is obviously going to be much bigger than the 30 degree one, because the 60 degree one is going way, way up in the air. So it's got a lot more time in the air. So that's why T30 is less than T60. Now, the height, again, obviously, the height for the 31, since it's super flat, is going to be much less than the height of the 60. So that's why it's that. That's why the answer would be E. Now, this guy was trickier than it needed to be. What you have to do here, really, is you just have to take all of these equations, the 4 equations, and you have to plug in 2 seconds. So, Vx, no matter what, is going to be 5 meters per second. Vy, however, when you put in 2 seconds, ends up giving you 3 times 2 is 6, minus 6, is 0. So that ends up being my velocity. It's completely in the x direction. Okay, now A, or AX rather, you're going to plug in 2 here, and you're going to get a x component. That's going to be -5. And you're going to plug in 2 here, and you're going to get a y component that is 6. So this is the only one of those choices that has an acceleration that is back and up. Ta-da! Okay. Now this one, it gives you some data, all right? And it really is just asking you to make a line of best fit, which we do. And then once you've made your line of best fit, which all of them basically are the line of best fit, you're just going to find the slope, which is going to be down 17 over 6. And when you do 6 divided by 17, or 17 divided by 6 rather, it gives you roughly -3.1. Okay, this one. The velocity v is a function of time for a ball moving along x-axis is represented in the graph. Which of the following statements accurately describes the motion of the ball? Well, here were our choices. It says the ball is initially moving in the negative x direction at 3 meters per second. So, check. It then says slows down uniformly for 6 seconds, comes to stop, and then moves with increasing speed in the negative x direction. So that's where B kind of starts to fall apart, because it slows down for 6 seconds till it gets to 0. But then it begins to move in the positive x direction. So it says negative x direction, so these are already gone because it has to be moving in the x direction. This one's gone because obviously it's accelerating, so it can't be constant acceleration, positive. Okay, so ball's in constant acceleration and moves in the positive x direction for the entire 10 seconds. So that is not true, because if we look at the graph, it's moving. Simple answer is it's going to be this one, because that's a lie. It's going to be this one because it's moving from the negative direction at 3 meters per second. 6 goes, because remember, this is a velocity versus time graph. Okay, last question. This is one of those questions that it's so easy it's hard. What do acceleration and velocity have in common? Well, they both have direction associated with them. So they're both vectors. So hope this helped. I understand that some of the explanations may not have been as good as others. So that's what we'll end up using Monday for. So obviously I'm assuming you guys will have some questions about it, and we'll deal with them on Monday. Okay, so This will be posted now. Look for the answer to the other two questions that I posted on the Google feed or on the Google Classroom sometime either later today or tomorrow. They'll definitely be up by tomorrow afternoon. And then at least we'll have something to talk about on Monday. All right, I will talk to you guys soon.